Hi everyone, I'm Stephen Weinkoop and welcome to today's webcast. Today we have some amazing information for you about performance tuning, where to look for performance issues, kind of what SQL statements are kind of suspect, the architecture issues that can come up, all sorts of really great things. Craig Mullins is joining us today and talking about some of these things and really giving you some guidance on where to look and what types of things you can tune and some really common mistakes. I have to say, as we're kind of going through the presentation, I learned an awful lot about what types of statements kind of have some frivolous information in them and what types of things are being done and what you can do to avoid those issues. So just a lot of really great information here. When you're done with the webcast, don't forget there's a survey link and you can let us know what you think about the webcast. And also there's a resource center available to you where you can download all sorts of other materials and get more information about different tools and different services and things like that that are available. So just all sorts of really great stuff. So as you watch the webcast, kind of think in a SQL kind of way, right? So be thinking about the different things that you're seeing, how they apply to your environment. Doesn't matter if you have a mixed environment with DB2 and SQL Server or just SQL Server or just DB2. There's an awful lot of information here that pertains on a very general basis for tuning your systems and understanding what's going on underneath the covers. So check it out, enjoy the webcast. We hope you enjoy it. And of course, head to the chat room, ask questions there, and we'll be sure to get you answers and make sure you have the information you need. Enjoy the webcast, and until next time, I will see you online.
Hello, and welcome to today's webinar, sponsored by Datavail, the DBA services company. My name is Craig Mullins, and I'll be talking to you for the next 45 or 50 minutes about best practices for optimizing DB2 performance. Some of you may know me. I'm President and Principal Consultant for Mullins Consulting, and I'm a DB2 practice consultant with Datavail, helping them to build their DB2 practice. I've got a couple books, DB2 Developer's Guide and Database Administration, and Datavail is good enough today to have some of these available for a raffle to folks who have attended the webinar. Before I move along, I also want to briefly mention that even though today's webinar is focusing on DB2 and DB2 for ZOS at that, a lot of the information that I'm going to be covering today is broadly applicable to any type of database. However, the options and how you go about doing it change. So this information will be useful to you whether you're using DB2 for LUW or Oracle or SQL Server, but mostly if you're using DB2 for ZOS. So with that said, let's take a look at some of the high-level issues in terms of optimizing DB2 performance. And first of all, we have the tuning progression. And this is where you're confronted with a problem and you don't really know where to start looking. And usually the way you're confronted with this problem is someone comes screaming into your office yelling, "There's a problem with DB2." You know, they never come in saying, "Well, there's a problem with this horrible code I wrote. Could you help me?" And therein lies the rub. The database is guilty until proven innocent instead of the other way around. So if you have that type of an issue, this is the resolution steps you take. Start with the application, move to the database, then to the subsystem, and out to the environment. We start with the application, SQL, host language code, because that's where most of the problems reside. Then we move to the database if we don't find it in the application. Things like indexing, organization, do we need to run a reorg? Hopefully not a design issue, but possibly that as well. If we don't find the issues there, we move to the subsystem, the zparms, memory locking, IRLM, those types of issues. And after that, we've kind of exhausted the DB2 specific things, but the environment where DB2 runs can also have some issues in terms of performance. So you might want to look at the way it's set up to work with the network or your transaction monitor, how you're interoperating with the web or what have you. So that's our tuning progression for problem resolution. Some other basic rules for DB2 tuning, we've got the 80-20 rule. And you've probably heard of that before too, because it's broadly applicable across a range of disciplines. When you look at it from database performance tuning, you really should see it as maybe 80% of the results coming from 20% of the effort. Or alternately, 20% of the applications are causing 80% of your problems. And most DBAs know who those bad boy applications are. The nugget of information you can take out of this is that you can optimize your ROI from a tuning perspective by focusing on the 20% that's causing most of the problems or that will deliver most of the results. In other words, don't boil the ocean. Next, tuning is an iterative process. You want to tune one thing at a time. Uh, consider what you might do if you're presented with that problem with DB2. There's a whole lot of things you could do to fix issues. You could say, well, let's tweak this SQL, add this index, change this zparm, and reorganize this table space. Well, any one of those things might be a valid attempt to optimize performance, but you don't want to do them all at once and then see if any of it helped. Do them one at a time. Focus on the one that you think is the most likely, perform that optimization, and then test to see if it helped, see if it hurt. Because if you add 4 or 5 things all at once, 3 of them may have helped, 1 of them had no impact, another one may have hurt, but you don't know which is which unless you're doing things iteratively. Also, keep in mind what tuning is. All tuning optimizes at least one of these 3 things: CPU, I/O, or concurrency. We want to be reducing I/O, reducing CPU, and increasing concurrency. If we're making a change and it doesn't do one of those 3 things, fine, it's change management, but it's not performance tuning, because these are the 3 things that impact performance. A couple more general things to remember when you are tuning DB2, tuning databases. The general rule of almost never say always or never broadly applies. There are times where things are usually a certain way, but you really should not say always or never. And even this rule follows that by saying almost never say always or never. Don't panic and remain humble. Tuning, when there's a performance issue, can be a very strenuous and stressful activity. Remain calm as much as you can. It will assist you as you go through the tuning process. As much as you can, design performance from the beginning. It's much easier to keep that in mind as you build your application than it is to just throw it into production and tune afterwards. I mean, let's face it, every application, if it's only running on a couple hundred rows in test, is going to run well. You need to design it for the thousands or even millions of rows that you're going to fit into your application in production. And the earlier you do that, the better. Finally, always remember the cardinal rule, and that rule is it depends. If you are a developer, you've heard your DBA say that. If you're a DBA, you've said it. And it's fine, because performance optimization is very complex, and it's something that isn't really easily explained in a simple manner. Your implementation, your situation, your exact requirements are going to vary. So whenever you have the urge as a DBA to say it depends, make sure you follow up with what does it depend upon. If you can't answer that question, then you really aren't being very helpful. I mean, it depends is not an answer to performance issues. What it depends upon can be. Okay, now if you remember back to that performance hierarchy chart that I had earlier, where do you go looking for a problem? We're going to dig into each of those 3 primary things from a DB2 perspective, starting with the application code in SQL. And as I said, most experts agree that's where the majority of performance issues arise. Typically, the numbers put it as high as 70 to 80% of performance issues are caused by the code. With that in mind, keep all of these rules in mind. Although simpler is better from an understanding perspective, complex SQL is where the efficiency arises. So put the work into the SQL. Build the SQL up into something that allows the optimizer to do its job and optimize access to data, instead of splitting it apart. When you split it apart, okay, maybe it's easier for you to understand as a developer, and that could have benefits if you come in at 2 o'clock in the morning, bleary-eyed trying to solve a problem. But if performance is your goal, putting the work into the SQL, letting the DB2 optimizer optimize that is the way to go. No matter how good you write code, you won't out-code the DB2 optimizer. Always provide join predicates. When you are doing joins, make sure that you have a path from table 1 to table 2 to table 3 in your on clause or your where clause. If you don't, and there's no way of DB2 to match up predicates between 2 of the tables, that's a Cartesian product. That's generally a bad thing. It's a bad thing because it takes all the information in one table, joins it to all the information in another table. It is consuming a lot of resources, not really giving you any additional information, and probably giving you the wrong answer to the query. Now that being said, Cartesian products aren't always bad. They're bad when you force DB2 to do them. When DB2 decides that maybe a Cartesian product is the best way to come across with the final result answer set, that can be valid. And usually where you see this is in data warehousing, star join type of queries. One big fact table, a lot of little dimension tables. DB2 can decide, let's join these dimension tables together even though we don't have proper join criteria for them. And what we're doing there, or what DB2 is doing there, is reducing the intermediate result sets, which can improve the performance of the query. We want to favor stage 1 and indexable predicates. I'll talk about stage 1 and stage 2 on the next slide. Just remember stage 1 better than stage 2 for right now. Indexable predicates better than non-indexable predicates. An indexable predicate has the capability for DB2 to apply an index to resolve it. Non-indexable predicate will never use an index, even if there's an index that is created on that particular column, because the predicate by design is not indexable. These are all listed in the manual, and again on the next slide we'll get into that. Avoid table space scans for large tables, usually. Now, table space scans are when you have to read every page in the table or a range of pages in the table to get the answer. And they're generally going to be less efficient than indexing. But again, this is not an always, because if you're going to, say, produce a report of all your customers, you're going to read every page in the customer table anyway, so a scan might be the way to go about doing it. Again, too, if you have a very small table, you've only got a few pages, reading the entire table space can reduce I/O instead of going to the index and then reading the index pages and the table pages. So it's not an always, but it's a usually. Big red flag if you see table space scans, investigate further. And then avoid sorting when possible, whenever you can. If you can remove a sort, do so. Building indexes for order by and group by. Not using distinct in your select list unless you absolutely need it. Favoring union all versus union. Keeping in mind, union all will not sort to remove duplicates. Union will sort to remove duplicates. So if you don't care about duplicates, or there never could be duplicates, union all improves your performance. Okay, now I said I'd talk about stage 1 and stage 2, and that's on this slide. Basically, stage 1 and stage 2 is just a way of describing predicates as to where they're applied within the DB2 address space. Data gets read from DB2 into the buffer manager, passed to the data manager, passed to the relational data services, and all three of these are components of DB2. After RDS, it goes to the results into your program. If the predicate can be applied at the data manager level, it's stage 1. If the predicate has to be applied at relational data services, it's stage 2. Stage 1 predicates outperform stage 2 predicates. Why? Because less data needs to be passed from one component to another of DB2. The less data that goes along these pipes, the more efficient your query becomes. So favor stage 1 over stage 2 predicates. Again, same way we favor indexable over non-indexable. Okay, how do we do that? Well, you have to understand where and what these predicates are. Every time you go to a new version of DB2, you should just hunt down the Managing Performance Guide. Now, sometimes these manuals change name, but you want to find the Performance manual. For version 10, it's SC192978, and there's a table starting on page 269 that lists all the indexable and stage 1 predicates. Print this out, give it to all your developers. Tell them stage 1 better than stage 2, indexable better than non-indexable. It'll do a world of good for your performance. Okay, stage 3. There's no real official stage 3, but I like to refer to it as stage 3 because I think it helps to put it in context as to how bad it is. Stage 1 better than 2, stage 2 better than 3, with stage 3 being, instead of putting the predicates in your SQL, you move them into your program and you filter there. That's more data moving along the pipe that sends the data to your program. So again, 3 worse than 2. So anytime you don't put the predicate in the SQL, but you put it in the program, think of that as stage 3 and repeat the mantra. 1 better than 2, 2 better than 3. We'll have a 4 in a moment. As you go through and write your queries, ask only for what you absolutely need. And yes, that sounds like simple advice, but I can almost guarantee you, I can walk into just about any shop in the country, or maybe the world, I should say, and find examples where this isn't followed. Retrieve the minimum number of rows, retrieve only the columns required. Minimum number of rows means code appropriate where clauses. In other words, avoid stage 3. Only the columns required means put into your select list only those columns you absolutely need. Now, sometimes that gets shortened to don't code select asterisk. And that's good advice, but that's really not enough. That's not the reason I'm talking about this from a performance perspective. Every column you put in your select list requires a little bit of overhead as it gets moved from the database into your program. The fewer columns, the less overhead. Sure, it's a small amount of overhead, but think about an SQL statement that runs hundreds or thousands or millions of times a day. That little bit of overhead each time it runs gets added and added and added till the little bit of overhead becomes a lot of overhead. Now, what am I talking about here? Let's look at an example. What's wrong with this SQL statement? We're explicitly naming columns, last name, first name, job code, department. From the employee table, we've got predicates. We're filtering out job code. We're filtering out department. Well, the answer is hinted at here in what's bolded, job code and department. Why are we asking for things we already know? Job code equals A. So why is job code in the select list? It's never going to be anything but A. We just told DB2 to only give us A. So if we know that, why make DB2 bring it from disk into the program? Same goes with the department. It's equal to MIS. It's not going to be equal to anything else because that's what we put in the where clause. I see this type of thing all the time. And again, it's not a huge issue unless this thing is running an awful lot in your programs. And, so if you're doing this in Spoofy or you're doing it as a quick one-off query, not a big deal. If you put it into a program, I think it is a big enough deal where you really should remove the columns from the select list because that adds up. Avoid black boxes. Another good piece of advice. What's a black box? Okay, what is a black box? It's where you code all of the SQL for your application in one program, the black box, and you make calls to this black box instead of writing SQL in your programs. And usually this is implemented because managers don't want to train all the developers to write SQL in their programs, or they think that there's some kind of efficiencies involved. This is a bad idea for a lot of reasons. Number one, you're coding a black box as an access path to data, and that's what SQL is. It's the access path to your data in DB2. Learn how to code SQL is better than learning how to access a black box. Also, the human nature being what it is, the people who are coding the black box are going to take shortcuts. What do I mean? Well, think about the rules that we just talked about. Minimum number of rows, minimum number of columns. If you are accepting requests from people as you write the black box, you're going to see things where the requests are returning similar data. Maybe you're returning customer data, and Team 1 needs 3 columns, and Team 2 needs 5 columns, and Team 3 needs all 30 columns. Human nature being what it is, if everything else is the same, you code one query returning all 30 columns. You pass 3 to the ones who need it, 5 to the ones who need that, and 30 to the ones who need that, instead of writing 3 separate SQL statements. What you just do, you designed bad performance by design right into your applications. So I rarely, if ever, see black boxes that don't take this type of a shortcut. This is why I like to refer to black boxes as stage 4. Even worse than filtering in your program is putting the code into another program. The other thing to keep in mind with the black box is you're adding overhead because there's path length, CPU that needs to be executed to find the query to execute and move the data back from the program to your program. So there's additional work that's being done that if it was coded right in your program wouldn't be being performed. If you're interested in learning more about black boxes and my thoughts on them, at the bottom left-hand port of this slide, you can see a link to an article on that topic out on my website you can read through. Okay, Optimization. Everyone should be able to look at this slide and briefly describe what's going on here. So what is going on here? Well, we've got the DB2 subsystem in the middle, and inside of the DB2 subsystem is the optimizer, which lives in the DBM1 or the database services address space of DB2. In the optimizer are these query cost formulas that get applied to SQL statements. So coming into the optimizer, we have our SQL statements, we have other system information, and we have statistics from the DB2 catalog. What is this other system information? Well, it's things like the amount of memory you have, the type of processor you're running. DB2 uses that so that it can help make some decisions about the access paths that it formulates. So it reads all this information in, applies the query cost formulas, and out the other end come the optimized access paths here in this red box. If we say explain yes, DB2 populates plan tables with information about all of these access paths. Now, there used to be just the one plan table, then they added the statement table and the function table, and then a couple releases ago added multiple other tables so you can get lots of good information. Usually this is for people who are using the visual explain capability in Data Studio, but you can query them yourselves if you want. So there's a lot of good information in the plan tables. Whenever we're in production, we bind explain yes. There's no reason to bind with explain no in production. All that does is blind you as to what the optimizer chose. Okay, the other thing here is this optimization hint. You can give a hint to the optimizer in DB2. And what that is to say instead of using or figuring out a new access path, use this old access path. And that's gotten easier as of DB2 version 10, instead of the old way we had to map to plan tables in order to get that. Now we can have that done in our optimization tables. At any rate, it's also better than some of the other DBMSs. I believe the way you do a hint in Oracle, excuse me, is to say, put a comment in the SQL that says use nested loop join here. DB2 doesn't allow that. It's basically go to a different access path. Okay, if there's all this good information in the plan table, we should be able to go in and analyze it. And all the questions that are shown here can be answered by looking at plan tables. You know, was a hint used? Was an index used? If so, one or multiple? And so on and so on and so on. All these questions have data in the plan table that can be answered. The key to doing explain analysis is the stuff that just appeared here in the middle. You need information about the SQL text and about the statistics and about the DDL and the way that the DB2 objects are set up, so that you can then say, here's the statistical information, here's the SQL, and here's what DB2 chose. And you can see, is this right, is this wrong, do we need to do some tweaking or tuning? There's other stuff, the stuff that showed up in red here, that can impact performance but also doesn't show up in the plan table at any rate. If you've got a trigger or if you've got referential integrity or constraints, all of these things also get applied to data as SQL operates, and it can impact performance. So you need to keep that in mind. But a lot of good information in the plan tables. You should be analyzing them regularly. And of course, another significant performance related issue is locking, and you can do an awful lot to improve performance by modifying your behavior in terms of how you issue commits. The first thing you need to think about is deadlocks, and deadlocks is basically where I have a resource 1 and want resource 2. You have resource 2 and want resource 1. Typically a page, could be a row. And one of us has to be killed in order for the other one to get what they want. So the general idea is to avoid deadlocks. DB2 does deadlock detection in the IRLM, and it will, once it detects it, figure out which one of the tasks is better to kill and kill that task, let the other one process. But everything that the task that has to be killed has done to that point is basically wasted. So we're improving concurrency by minimizing or eliminating deadlocks, and one thing we can do there is to code the modifications in our program in the same sequence regardless of the program. So instead of just mapping it out and coding the modifications where they lie, save them up within the unit of work and issue them all in the same order: table A, then table B, then table C, then table D. In alphabetical order by table name, or if you've got another order that makes sense, fine. But do it in the same sequence. That way, it will minimize the times I'm going after A then B and you're going after B then A. We're both going after them in the same sequence. The second thing you can do from a locking perspective is to minimize lock duration. The longer amount of time that a lock is held, the more is the possibility that someone else may try to access that data while it's being locked out from their access. One of the things you can do there is hold all of your modification statements until as close to the end of the unit of work as possible. In other words, right before the commit. So you do all your work, then insert, update, update, issue, delete, insert, merge, commit. Instead of stretching them out throughout the whole unit of work and holding the locks for longer periods of time. That'll minimize the amount of lock contention you have, improving concurrency. Always plan and issue a commit strategy. You should, after so many inserts, updates, and deletes, or after so much time has gone by in your batch program, issue a commit. If you're not taking commits, you will see timeouts and deadlocks in your system, the 911s and 913s, and generally it won't be for the program that isn't issuing commits. It's just going to happily go out there churning through data, holding locks, causing everyone else to have lock timeouts happening on them. So make it a regular thing that you do in all your batch programs is to push a commit into them and to monitor all those programs before they go into production to make sure that commit's there. We can encourage lock avoidance with isolation, cursor stability, current data no, and then our read-only cursors will avoid locking, improving concurrency. And in certain circumstances, we can use an uncommitted read isolation, otherwise known as dirty locking, to avoid locking. However, you don't want to do that if you absolutely want to guarantee 100% valid, accurate results, because with dirty reads, you're reading data that hasn't been committed and may never find its way to the database. So if you're doing account balancing or something like that, banking transactions, you don't want to use dirty read. But maybe if you're doing averages over lots of rows where a few more rows being in there wouldn't harm that average too much, a dirty read can make some sense and improve performance. Other programming issues, don't spend a lot of time getting that SQL very efficient, which is a good practice, but then putting it into inefficient program logic. So finally tune it and then throw it in a loop that runs millions of times. Again, we talked about letting SQL do the work. Sign of trouble there is if you have, after your select, after your fetch, a lot of if, then, else, or case statements, take a look at them, because if that's a sign that you may be filtering in the program instead of filtering in where clauses. If you're only going to retrieve one row, go with a singleton select. And instead of opening up a cursor and fetching and closing it, consider adopting multi-row fetch. With multi-row fetch, instead of one row at a time, you're getting multiple rows at a time into an array in your program. And tests in the IBM Redbook show 50 to 60% improvement if you're doing 100 or up to 1,000 fetches at rows coming back at a time into your array. One of the other things, if you have an online transaction, you want to limit the amount of data retrieved to be a reasonable amount, but you also might want to consider optimize for one row to disable list prefetch. When you're using list prefetch, DB2 acquires a list of RIDs from a matching index, and it sorts them and accesses the data by that RID list. That can be somewhat efficient if you've got a multiple page transaction that would cause the user to wait for that initial data to be displayed. So if you say optimize for one row, DB2 eliminates list prefetch as an access pass possibility. So consider that for your online. Okay, at this point we've looked at a lot of application issues, but let's say we've gone through that and we still haven't found the problem. It's time to take a look at database type things. And some of these things we're going to talk about will span the database and the application a little bit. One thing is, be able to take a look at all this and understand the database structures. I'm not going to go into this slide and explain all the things on here for you. This is basically a map of the DB2 objects that can be created. But let's talk a little bit about some general table space recommendations. And universal table spaces are the way you should be going for your new DB2 table spaces. Should favor them over segmented and traditional partitioned. Remember, simple has been deprecated, no longer supported. Partition by range is a good idea for a large table space going to exceed 64 gig, but you don't have a suitable partitioning key, or range partition by range, when you've got that suitable partitioning key. Remember, what a universal table space does is it combines the best capabilities of the segmented and the partition table space into kind of one type of table space. In most cases, you want to limit yourself to one table per table space. Universal table spaces can only have one table per table space. If you really have to have multi-table table spaces, use a segmented table space. You can still do that there. But in general, you really don't want to do that too often because the utilities operate at the table space level. And if you load replace one table, you may find yourself having written over and replaced data in another table in that table space. And you want to avoid that type of thing. From an organization perspective, we want to make sure we're reorging our data appropriately. Run your run stats, new it as data volume changes, you add new data, and follow that with rebind with explain yes. And we'll talk about that in a little more detail in the next slide. You want to review statistics, or better yet, real-time statistics that will help you determine when to reorg. Look at your near and far indirect references, your leaf distribution, percent drop. For clustering indexes, look at the cluster ratio, near and far off positioning. And there are some guidelines, again, in the Managing Performance Manual that you can look to set some thresholds as to when it's time to kick off a reorg. This brings us to the 5 R's, and you may have heard this talked about as the 3 R's, but really there are 5 involved in it. And what this is how we schedule our maintenance of our DB2 table spaces. We look at real-time stats. You can still look at run stats, but the real-time stats are going to be more up-to-date for you and help you gauge when you need to run a reorg. When you hit the thresholds on your indirect references or your clustering, or any of the other things we talked about in the previous slide, you want to run a reorg for that table space. Once the reorg is done, you want to run a run stats. You can combine reorg and run stats and do an inline stats to kind of minimize the amount of times you pass through the data, but you're doing a reorg and a run stats. After you do that, you want to rebind. And we're running that run stats after the reorg so that the rebind has the accurate post-reorg stats so that we can get better access paths when we do a rebind. So the first 4 R's, real-time stats reorg, run stats rebind, and then we want to recheck. In other words, what did the rebind do? Did we get any paths that changed? Do they look better? Do they look worse? Do we need any other attention? Do we need to tweak some things? Or are everything good to go? And we want to do this regularly with our DB2 environment so that we are reorging when it makes sense to reorg and not reorging either too soon and consuming CPU to run a reorg that doesn't need to be run, or too late and running a reorg after access paths have degraded and our transactions and programs are starting to experience performance degradation. If we still have problem access paths, there's some things we need to consider. Were the statistics up to date? Did we run the right type of statistics and amount of statistics? And when the package was rebound, did we do it at the right time with those stats? And one of the interesting things is a lot of the problems that get reported to IBM as to bad access paths can be traced back to inappropriate statistics and sometimes even no statistics for certain of the tables. Kind of boggles the mind, but it is the truth. And again, if the problems persist, you can go out and change the SQL. You can use plan stability to go back to an access path that was better for you in the past. Tweak the SQL, so coerce the optimizer to do what you want it to do, or add an access path hint, or even go out and manipulate statistics, but that should only be a last resort. From a table design perspective, high-level guidelines, normalized as possible, third normal form as much as we can. But remember, performance more important than aesthetics. In other words, normalization is optimizing update at the expense of retrieval. Sometimes we do need to do some tweaking to the data structures to optimize retrieval, and that is something that as DBAs we sometimes need to do. In general, avoid the defaults. They're usually wrong. What I'm saying here is not setting up a column is not null with default. That's fine. What I'm saying is if you've got a parameter or an option and the default is left so you don't specify that parameter or option, that's a bad idea. Even if it turns out that the option you wanted to specify would have been the default, you're better off coding it and understanding what you're specifying to DB2. Use free space. There's two different types, %free and free page. Don't just let everything default, but put enough free space in there based on the volatility of the data. How frequently and violently is the data in here going to change? And put enough free space so that you, in between running the reorg utility, there is room for it to grow. Always use appropriate data types. If it's character, use character. If it's date time, use a timestamp or a time or a date, and so on. We want to match the date to the domain as much as possible. And in some cases, instead of using variable character data, you might want to consider compression. With variable character, you've got that 2-byte prefix that handles the length of the column, whereas with compression, it just compresses the entire row. So you might be able to, instead of saying variable character 50, say character 50, and turn on compression. No programmatic handling, and then compression of that character, but also compression of the entire row, so you save more space. Now, I'm not saying always, but I'm saying sometimes that's something that you can consider. You want to design your columns based on logging. DB2 logs from the first byte changed to the last byte changed. Unless it's a variable length record and the length of it has changed, then it's the first byte to the end of the row. Unless it's a variable length record and the record length hasn't changed, then it's the first byte changed to the last byte changed. That's a lot to remember. Don't worry about it, just follow the rules listed here. Put your infrequently updated non-variable columns first, your infrequently updated variable columns after that, and your frequently updated columns at the end. Also, put columns that are frequently modified at the same time next to each other. So if for whatever reason middle initial and phone number are modified at the same time, first name, middle initial, phone number, last name is perfectly valid to optimize logging. It might make a data modeler pass out, but it's the right thing to do from a performance perspective. Now you may be saying, oh, didn't DB2 version 9 add this new row format that moves all those variable columns to the end of the row? And yes, it did, and that kind of messes with the ruling here, where I'm saying follow these 4 bullets under the first big bullet. But still, this is the best that you can do with the reordered row format. DB2 is going to juggle them around for you. You still want to try and get your infrequently updated non-variable columns to the beginning of the row. Use declarative RI instead of program RI. Not going to go into that. That's general goodness, motherhood and apple pie, right? We don't want to put it in the program. We want to put it in the database. Designing indexes, a proper indexing strategy can be one of the biggest things you do for optimal performance. However, it's also one of the things that we tend to get wrong. We should index by workload, not by object. But usually what we're doing is we're creating new databases, is we'll create a table, create a couple indexes, create a table, create a couple indexes. And we do that all before we have access to the SQL that's going to be run against it. We should have some idea of the workload going against our tables before we create our indexes. There are certain things you have to do. Unique and primary key constraints, usually for foreign keys, good idea to have in indexes. Then you really want to look at your heavily used queries, your important queries, and put indexes on those. Heavily used a lot during the day, important, maybe used by your boss, used by the CIO. Some cases overload columns so you can get index-only access. Not always, remembering that when you impact one index for one query, it could be used by other queries and cause problems there. Index to avoid sorting, we touched on that earlier. And generally keep creating indexes until the insert, update, and delete implications begin to be felt. You just index till it hurts, in other words. You want indexing to optimize your access. Indexing, on the other hand, will cause a degradation to your modification because you have to modify the table plus all of the indexes that are designed for it. So no artificial rules saying only 3 or only 5 indexes. Keep indexing until such time, or right before, if you can, the modification begins to get hurt, or if you can't, do the one, you start seeing the impact of the modification, and then you would back off the least used index. You can check out this column, last used in sysindex space stats, to see when an index was last used if you want to try to winnow out indexes that aren't used. Okay, we looked at the application, we looked at the database. Let's move off and look at the subsystem. First of all, this is the layout of what a DB2 subsystem looks like. Multiple address spaces. And you can read this and look at it as well as I can. Let's move on and dig into what's under the covers here. And we've got memory usage by the subsystem. Relational databases love memory. DB2 is no different. There's 4 types of pools, if you will, or memory structures that DB2 uses to cache data and information, allowing us to reduce I/O. That's buffer pools, RID pools, EDM pools, and sort pools. Let's dig into each of them. DB2 has 80 buffer pools. Use them. Spread your work around. You know, the old days there was guidance that everything should be in BP0. That's old advice and not the case anymore. You really want to be mixing your workload up across the buffer pools. I'll give you some information when we look at the thresholds on the next slide. You might want to consider reserving a buffer pool for tuning, move problem objects there and isolate them. You can see the access to that buffer pool then, and then once you've resolved the problem, move it back to another buffer pool. In general, monitor the hit ratio, which is this formula here, get pages minus pages read, which is synchronous and asynchronous, divided by get pages. The higher this ratio, the better. That means it's the number or percentage of times that a page is found in the buffer pool. Look at the thresholds. What am I talking about with thresholds? Well, this slide shows them. The lighter color, purplish, is variable. The darker color, black, is fixed. And if you look at these variable thresholds, we'll start with deferred write. This is reached when 30% of the buffer pool is allocated to unavailable pages. That means they've either been updated or they're in use. When DB2 reaches this, he'll start scheduling write IOs to externalize the data pages to disk. The default for this is 30%. Probably too high. One of the things that is a good general recommendation is to look at ratcheting this value back so that as DB2 makes modifications, he's trickle writing instead of storing them all up and blasting them all out periodically. We also have VWQT, which is the vertical deferred write threshold. And you can think of that as basically the same thing as deferred write, but at the data set level. So by default, if 5% of the pool is allocated to one data set, DB2 starts scheduling write IOs to externalize data pages. Again, 5% probably too high. The other thing you'll notice is as of version 9, the defaults were lowered here, and in my opinion, they weren't lowered enough. Then you've got the sequential steal thresholds, VPSEQT, VPPSEQT, VPXPSEQT. And sequential steal threshold by default is reached when 80% of the buffer pool represents pages for sequential processing. When we reach this, DB2 steals a sequential page before stealing a page from a randomly accessed page. So what you can do here is if you've got mostly tables that are being accessed sequentially, a lot of scans, a lot of prefetch going on, look at ramping up the sequential steal threshold. You've got a lot of random access, look at ramping it down. And then you've also got the parallel sequential, which is sequential operations for parallel tasks, and the assisting parallel sequential, which is for data sharing. That's valid through version 10. Version 11 of DB2 deprecates the data sharing parallel operations. Okay, now there are fixed thresholds here, which are shown in black. Now these can't be changed. All the ones in purple we can change. The ones in black, no. First we have prefetch disabled, and that's at 90%. When that happens, DB2 will no longer initiate prefetch operations and cancel any that are in progress. Bad, we don't want that happening. 95% is data manager critical. That's when that percentage, by 95% of the buffer pool pages are unavailable. When we reach that, DB2 will access the pages in the pool once for each row that is retrieved or updated in the page. In other words, you're going to be retrieving or updating several rows in one page. That's going to cause several page access operations. Again, not a good thing. Finally, at 97.5%, if the buffer pool pages are unavailable at that percentage, you get the immediate write threshold. This means DB2 will write updated pages as soon as the update is complete. The write's synchronous, not asynchronous. It's going to cause a large increase in the number of write IOs performed by DB2, and you really need to avoid this. Okay, so you got 3 fixed thresholds, can't change them. How do we tune in that situation? Well, this is where you use your multiple buffer pools. Look at moving some of the objects out of the buffer pool that's being stressed into another buffer pool that has objects in it that are not being stressed at that point in time. Look at your scheduling, look at your transactions, see when they're run at the same time, and look at moving these things out and then tuning the variable thresholds and allowing you to not meet these fixed thresholds. The other option, of course, is to increase the size of the buffer pool, but you have to make sure that you've got sufficient memory to back that up, because you definitely don't want a page to disk for your buffers. RID pool is used for all record identifier processing, RID processing, and you can see the types of access paths here in light blue that require RIDs. You can change the size of the RID pool. The default's 4 meg, but it can be increased. You can disable access paths listed here by specifying a RID pool size of 0, but this can degrade the performance of any programs that were previously bound with a non-zero RID pool size. So if you do make this change back to 0, always rebind those programs. Maximum size of the RID pool is 1,000 megabytes, and all concurrent processes share this single RID pool. If you get RID pool failures, because there's not enough space, you will get degradation as DB2 reverts to table space scans for those types of accesses. EDM storage used to all be in one pool, but now we've got multiple pools as of version 8 and extended in version 9. What is in the EDM? It contains control blocks that are used when DB2 is running programs. So it'll have the DBD, which has all of the structures for the objects in the database that has to be moved to the pool so DB2 can access them. It has package tables and cursor tables for your packages and plans, as well as skeletons for both of those, so you can build new PTs and CTs out of the skeletons. And it has the authorization cache, it has dynamic SQL preparation, and it can have some free pages. In general, you want to be looking for an 80% efficiency. In other words, only 1 out of 5 times would you ever need to load a DBD, an SKPT, or an SKCT into the EDM pool. So that's a good thing to shoot for. Now, as I said, these things are broken up, not all in one pool anymore, so that's good, makes it easier to tune. We've got an EDM pool, which is below the 2 gigabyte bar, introduced in version 8, which stored the CTs, PTs, and skeletons. As of version 9, we get the EDM skeleton pool, which breaks out the skeletons to their own pool. Version 8 also introduced the DBD and the statement cache as separate pools, and they're above the 2 gigabyte bar. The sort pool, there is a sort pool for each user, and you can specify the maximum size. In general, to optimize sort and sort pool usage, minimize the amount of data that needs to be sorted. DB2 uses a tournament sort unless the sorted records are greater than 4075, and then it reverts to a tag sort. The tournament sort, more efficient than the tag sort, so reducing the size of the sorted record, which is the keys being sorted plus the RIDs, will give you a more efficient sort. Sorts that don't fit into the sort pool overflow to a work file. Increasing the size of the sort pool, therefore, can improve the efficiency of the sort. Make sure you have sufficient physical work files for your sorts. And another thing to keep in mind is the better sorted the data is originally, the more efficient the sort will generally be. Okay, let's move on and look at logging. And keep in mind, DB2 is only going to run as fast as the log. All of your modifications have to go through the log. So configure your system with dual active logging, with each log defined to separate devices on separate channels. That way, if you get a hit to the log and the log fails on one of the devices, the other one is up and running. With single logging, if the log fails, DB2 comes down. So we don't want that at all. Another thing you can do is to ensure rollback processing is retrieving log data from disk if possible. So if we issue a rollback and we've done so much modifications that we had to archive the log, and we're doing archiving to tape, the rollback requires the operator to go back and mount that tape. And that can be inefficient, especially if you're not using a tape silo or something like that. So you can consider archiving your logs to disk, at least for the beginning, and then over time use HSM to migrate the logs to tape. That way your archive logs will be on disk for a period of time such that anything that's active that might need to access the data in the archive wouldn't have to be slowed down by waiting for tape access. Okay, we've also got system checkpoints. Periodically, DB2 will pause long enough to take a checkpoint and write out records, and it has information about currently open units of recovery, open page sets, exception states, and it uses this to speed up the restart process for if DB2 goes down and comes back up. Taking a checkpoint also causes DB2, it's writing out those pages, so you really want to have the checkpoint frequency set up so that it's basically every 5 minutes during peak processing time. You can set this using either number of log records written or number of minutes. In general, since as of version 7 we've been able to do it with minutes, most people just say 5 minutes and are done with it. The IRLM is lock tuning. You can set the max CSA value if you know locks per user and max users, which are ZPARM settings that should be set up for your environment. Multiply those by 250 and that should be your max CSA usage. There is an option on the IRLM to do tracing, iTrace. Do not use it. iTrace equals no is the way to go. If you say iTrace equals yes, it's very, very slow. It will cause system resource issues. If you need lock information, use the DB2 lock tracing. Start a trace for locks. And deadlock detection is also done by the IRLM. Okay, so if we've looked at the application, then the database, and then the system, it's still possible we could have issues, but they're not going to be within DB2. You can have operating system issues and transaction and networking and hardware and all these different things which DB2 interoperates with that can still cause issues. Now, all of this could take another hour-long presentation talking about each of these issues, so I'm not really going to go into them other than to say once you've gone through the application, the database, and the DB2 subsystem, you still may have tuning issues that impact DB2 that are not caused specifically by DB2. So keep that in mind. But in general, if you start at the application, move to the database, from there to the subsystem, after that look at the environment, in that order, do one thing at a time, iterative process, and then you find you can tune DB2. If you are boggled by the enormity of that task and you maybe not be able to do all of that, one of the things you might consider is remote DBA services, such as offered by Datavail, the sponsor of this webcast. Datavail offers remote DBA services and operates 24 by 7 around the clock across the globe. Got delivery centers across the globe that can cover the time zone where all the clients operate. So one of the benefits of DBA services is that there's always a DBA available around the clock actually there working. So you've got that problem at 2 in the morning. You don't have to wake up a bleary-eyed DBA and hope that they can solve the problem when you've got someone who's right there ready to staff the issue. Datavail has performance management experts. You've got multiple DBAs focusing across multiple DBMSs with hundreds upon hundreds of man-years of experience. You can use the customer's preferred monitoring tools. Datavail has their own monitoring tools that they can leverage in those situations, as well as a ticketing system for interoperating with DBAs at Datavail. So all of the tools that are necessary in order for you to do your IT service management are there and integrated with your environment when you deploy Datavail's DBA services. It truly is a managed services solution, and Datavail is the world's largest pure play database support company. When you take on Datavail services, what you're really getting is a small slice of a very sophisticated operation. It's been built over a decade by people, as I mentioned, with hundreds of years of experience in IT operations and database administration. A few statistics, more than 250 customers, more than 350 DBAs across multiple tiers, across multiple DBMSs. Headquartered in Broomfield, Colorado, right outside of Denver, with offices in Seattle and New York and delivery centers also in Mumbai and Bangalore. The company's growing, it's mature, and it has a proven delivery model. So one of the things that you ought to look into is, you lose a DBA, maybe instead of hiring on another full-time DBA, you call up Datavail and augment your staff with the Datavail services. Or if you're looking to outsource the entire database operation, Datavail has the ability to do that, or to take on your DB2 and database-focused projects. My name is Craig Mullins again. If you have any questions after this that rise up, you can contact me at this email, or you can ask your questions now through the webcast services here on the Schwag website. That's all I have for you today. I want to thank you for joining us. And again, if you have questions, feel free to email me or send me the question right now over the Schwag services. Thanks, everybody.